We're about to study complex impedances which describe the behavior of inductors and capacitors with AC waveforms, which are some form of sinusoid. And before we study that, we're going to first have to understand what the phase relationships between sinusoids is. So now let us consider two AC waveforms here. So V1 is equal to 10 cos omega t plus 45 degrees, and V2 is 8 cos omega t minus 45 degrees. And this is what those waveforms look like. So let's understand what these mean. And so if we're looking at the first waveform, V1, we see that it has a amplitude or voltage magnitude of 10, and so the peak value on the AC is 10. And then we have a phase shift of that waveform, and that phase shift is plus 45 degrees. And we know that a positive phase shift of a sinusoid means that its waveform shifts over to the left by the same amount. So in this case, it's 45 degrees. Now for V2, we see that the magnitude of the waveform is 8. So it has a peak value of 8. And its phase shift is minus 45 degrees. So that is a rightward shift of 45 degrees of the waveform. Now, together, those two waveforms are shifted from each other by a value of 90 degrees. Okay, so now let's look at what the phasor form is going to look like for those waveforms. So when we're looking at the phasor form, we just drop down the magnitudes. So we have a magnitude of 10 for V1, and in the phasor form, that's the number that we use, 10, and we bring the phase angle down, and it becomes 45 degrees. Okay? And then we do the same for V2, where we have 8 coming down to 8, and minus 45 coming down to minus 45. And then, when we draw these waveforms, we can draw them down here in the complex plane, where we have the real axis as the horizontal axis, the imaginary axis as the vertical axis, and the phase angle is as shown. So this is a positive 45 degree phase angle. The magnitude is 10, so that's the length of the vector. And then when we look at the V2, then we see magnitude of 8 and a phase angle of minus 45 degrees. So now, either looking at the time domain waveform on the top, the sinusoids, or in the phasor form on the right, we can apply the following terminology. So, we can say that the phase of V1 is 90 degrees higher than the phase of V2. So that means that we have a leftward shift of V1 compared to V2. So that is a leftward shift, and that is a shift of 90 degrees when we're looking at the time domain waveforms. Now at the same time, we can see that we have a counterclockwise shift of the waveforms in the phasor form, and that is 90 degrees as well between those two. So V1 is 90 degrees higher than V2 in terms of phase. We can also say that V2 is 90 degrees lower than V1 in terms of phase. Now, another piece of terminology is that V1 leads V2 by 90 degrees. So it's the same thing as saying 90 degrees higher. So we say that V1 leads V2 by 90 degrees. So again, that's a shift. It leads by 90 degrees, and again, that's leading by 90 degrees in both forms, time domain and phasor form. Okay, and then we can say that V2 lags V1 by 90 degrees. So now, when we're talking about lagging, we're talking about a rightward shift. So V2 lags V1 by 90 degrees. Okay, and then in phasor form, we're going in the clockwise direction. V2 lags V1 by 90 degrees. So now we're going to have a simple example to play with some of the concepts that we've been looking at so far. So now we have an example of three phasors. Okay, we have a V1, a V2, and a V3 as shown. So then what we want to do is put these phasors in the time domain form, and we're given that the frequency of the waveform is 100 Hertz. Okay, so let's look at the V1 phasor, and this is how we write it. So now we have to show the phase angle as a counterclockwise angle, okay, moving as we see in the red rather. But we were given the phase angle as 45 degrees moving from the negative real axis. So we have to convert that. So what we're going to do is go all the way across to 180 degrees and then come back 45 degrees. And that's what's shown over here. So it's 180 degrees minus 45 degrees, which will give us 135 degrees here as the angle. Okay? So then, the other two phasors are easy to write down. So V2, we have a magnitude of 10 and a phase angle of 30. So we can write that directly, 10 with an angle of 30. And then V3 is given with a magnitude of 8 that we've written. And V3 is directly on the imaginary axis. So it's a 90-degree shift from the real axis. So we say that it has a phase angle of 90 degrees. So then, to continue the solution, to put these phasors into a time domain format, we need to find a value for omega, okay? And we have to use F to convert omega. And how we do that is by using our equation, omega is equal to 2 pi f, and in our case, f is 100 Hertz, so we just plug that in, and then we get 200 pi radians per second as our omega. And then, to write it in, we're going to write V1 in its time domain form, and what do? We take the magnitude, okay, so we're taking the magnitude, the 7, we're putting in front of the cos, so that's a magnitude in the time domain as well. Okay, we take the phase, which is 135 degrees, and we put it in there as a phase. And then what we're missing is omega, which this is omega, okay, and then we get that from here, which we've calculated, and we put that in to that position, and then we add the t. Okay, it's a function of t. So that is how we construct our time domain representation from the phasor form. Okay, So then, it's fairly straightforward to repeat the process for V1 and V3, for V2 and V3. So 10 comes down here, the 30 degrees comes here, and omega comes here for V2, and then V3 follows the same pattern, 8 and 90 degrees. Okay, so now let's talk about how we're what the relationship between the waveforms are in terms of the phase. So let's consider V1 leads V2 by how many degrees? So what does that mean? So V1 is up here in green, okay? We've calculated that its angle is 135 degrees and it's leading V2. So we want to find out how much it's leading V2 by. So what we want is actually this angle right here. Okay? How much ahead of V2 is V1? Okay? So what we can do, we can write it out. Okay? So it's going to be 135 degrees minus 30 degrees, that's what V2 is, and that is equal to 105 degrees. So what I've drawn here is 135 degrees. Okay, so let's do the next one. Okay, so V1 leads V3 by what? Okay, so what are we looking at here? So we're looking at this angle right here. Okay, so we know V1 is at 135 degrees and V3 is at 90 degrees, and the difference between those two is 45 degrees. Okay, so then let's go on the other side here. V3 leads V2 by how much? Okay, so where's V3? So that's in red, and it's leading V2, so then we're looking at this angle here. Okay, so then we have V3 at 90 degrees, so 90 degrees, and then minus the angle of V2, which is 30 degrees. And that works out to 60 degrees. Okay, and then let's do the last one. So how much does V3 lag V1 by? So where's V3? So that's in red, and it's lagging V1. So now for this one, because it's lagging, we're going in the opposite direction, so we're going clockwise. So that's the angle that we're looking at. And so we know that V1 is at a 135 degrees, and minus 90 degrees is going to be equal to 45 degrees. So that's a little bit of summary about phase relationships between sinusoids, and a little bit of translating between phasor and time domain forms.